Hello, my name is Ronit, and this is my Physics 2212 Lab 4. So, some key concepts we need to understand for this lab are the node rule and loop rule. And basically, the node rule is that the current at any two nodes should be the same. The loop rule is that if a circuit diverges at some points, the sum of both of the divergence points should equal the total current that went into that divergence point. Ohm's law is I equals V over R. RC circuits is just the concept of having both resistors and capacitors in a circuit. Parallel circuits are when the resistances are summed linearly when circuits are in front of each other, back to back rather. And that's a series, excuse me. A parallel circuit is rather when two circuits are parallel to each other and basically at a divergence point, as I stated before, and therefore the resistances of those are added using 1 over R, and that 1 over R summation of all the resistances is equal to 1 over the total resistance. A resistor basically creates resistance in a circuit. A good example is a light bulb. Ammeter allows someone to check the current at two places in a circuit using two prongs on different parts of the circuit. Batteries provide a potential difference to a circuit, have a positive and a negative end, and a voltmeter allows a person to check the voltage at two different between 2 points on a circuit with the two prongs like an ammeter. And finally, a capacitor is a form of resistance where uh, electrons collect on one side and therefore push electrons on the other side rather than actually allowing electrons to flow through. So some important formulas, and I already brought some of these up: Ohm's law, parallel circuits, series circuits, node rules, and loop rules. Really the only new one is the lab specific equation that was given to us, and that is that the ln of the change in the voltage over the change in the voltage initial is equal to the negative time over RC. And RC is the time constant which we are looking for in this lab. So when I did the first part of the lab, I first predicted a current of 0.02 at both I1 and I2, and when I actually recorded those values, I found the same exact values. And so therefore I was right in my prediction. And if we move the ammeter prongs backwards, it still reads the same value. After the voltmeter is put in, the current still reads 0.02 amps, but the voltage reads 3 volts. And I also measured the potential difference at various different points in the circuit that were given to us in a image, and I named them based on the characters that were given to us in the image to specify the location. So those values are given right there. Okay. So observations: very little current flows through the voltmeter itself, and the overall current of the circuit is therefore relatively not affected by it. And the current we measured through the 10 ohm parallel resistor was 0.06 amps. The resistance through the 47 ohm resistor we calculated to be negative 48 ohms. The resistance through the 100 ohms resistor we calculated to be negative 102 ohms. And the resistance through the overall wire, since the difference in the voltage is 0 throughout, is 0 ohms. And similarly, the resistance through the ammeter, uh, since the difference is 0 in the voltage, in the current, we again get a resistance of 0 ohms. Basically, the equation we used here was R is equal to I over V, or resistance is equal to current over voltage. So RC circuit recorded values: when the light produced by the 10 ohm bulb turns on, it starts bright, then it dims to nothing. And when the capacitor is connected to the 10 ohm bulb, the light turns on again and then fades to darkness. When the capacitor was charging, the current in the circuit started high and decreased all the way to 0. And when the capacitor began discharging, the current quickly rose, then decreased all the way to 0. And these are the time measurements I had respectively for the 10 ohm and 20 ohm capacitors to charge and discharge. This is the graph I got, graphing ln of delta V over delta V O on the y-axis, and initial, and then time in seconds on the x-axis. And the line of best fit I got had a slope of negative 0.178, and the y-intercept was at 2.188. The voltage across the capacitor that they asked me to measure was 9 volts. All right. So then calculating both the slope and RC, uh, through simple calculations, not using the graph, we were given a resistance of 30 ohms, and we were given a capacitance value of 200 millifarads or 0.2 farads, and RC is therefore the product of the two, 30 times 0.2, which gives us 6. And then comparing that to the graph and what we can derive out of the slope of the best line, which we got to be negative 0.178, we can therefore use the slope equals negative 1 over RC equation, move it to become RC equals negative 1 over slope, and therefore get an RC of 5.617, which is very close to the value we wanted. Now finally, for the what if questions. If we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, the main difference would be that it would actually create some resistance, which would therefore affect the current passing through in the overall. And instead, in the ideal situation, in the simulator we use, the ammeter is thought to not create any resistance and simply check the current passing between the 2 points. So it would affect the current at the endpoint because it would be affected during the moving between the 2 points by the ammeter, and it would affect the overall. And the second what if question, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? To answer the second question first, an ideal model would predict the capacitor to reach full charge instantly, because we are assuming in the ideal model no resistance in the wire itself, or any of the voltmeters, amp meters, etc. And the truth is, if we used a real battery, there would be resistance in the wires. And also, we would lose a more realistic amount of energy to the bouncing around of the particles, so heat. And therefore, it would actually take somewhat longer than instant to charge up that capacitor. So, thank you for watching, and have a great day.